All right, hello again, method students. In this video, we're continuing on with our work on binomial probability and binomial distributions, but this time with an emphasis on developing a formula and understanding how to apply that formula for binomial distribution calculations. So we've seen in our previous video that when you try to work out calculations associated with binomials, what you often have to do is work out how many different ways a particular arrangement can happen. So we actually saw in the previous example 3, when we had to work out the probability of getting exactly 3 daughters in a family of 4, we had to think about all the different ways that you can get 3 successes out of 4 trials, right? Now, there's actually a formula that lets you calculate those arrangements. And it's really helpful for bigger calculations. So if you had a family of 10 children or something like that, and you wanted to know all the different ways you can get, say, 3 daughters out of 10 children, obviously that's going to be a much more complicated thing to draw on a tree diagram and write out the combinations. So this notation here, both of these things in the heading here, are read as n choose x. We use it in binomials as saying it's representing all the different ways, or the number of different ways you can get x successes from n trials. Right? So if n is your number of trials, x is your number of successes. Like I said, both of these notations mean the same thing. This is probably the more one you're likely to commonly see written in methods shorthand. So the way this calculation works, and it's not a commonly applied calculation. You usually will be allowed to use your calculator to kind of bypass this knowledge, but it's probably important to understand what this formula actually is. The formula says that it's n choose x. In other words, if the number of trials is n and the number of successes is x, that will equal, so the total number of combinations will equal n factorial divided by x factorial times n minus x factorial. Now these exclamation marks, like, they don't just mean to say it really loud. It doesn't mean like n. What it means is if the number is, say, 5, so it's 5 factorial, well, 5 factorial means you multiply by every whole number below it all the way down to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1, right, which is 120. 7 factorial would be 7 times 6 times 5 times 4. You get the idea, right, all the way down to 1. Now, just as a bit of an extra thing, let's just say, as just a practice run for applying that formula, say we were in a situation where we had 5 trials and we were interested in how many different ways can we get 2 successes out of 5, right? So 5 trials, 2 successes. Now we could try to draw out a tree diagram, right, with and try to identify all the different ways we can get 2 successes out of 5 trials. But if we practice using this formula, the formula says that it's n, the top number, so 5 factorial divided by, right, now the formula says it's x factorial on the bottom, the number of successes, so in this case 2 factorial, times n minus x, so the number of trials minus the number of successes, factorial. Now in this example that I've made up here, this would just be 5 minus 2 factorial, okay? So that would be 5 factorial over 2 factorial times 3 factorial. Right. So you can actually see that what happens on top is you have the number of trials as a factorial. On the bottom, you've got the number of successes as a factorial times the number of non-successes as a factorial. Now, when you go to work this out, you can actually write everything out in the full sort of form, what it means, right? So 5 times 4 times 3 times 2 times 1 on the top, divided by 2 factorial just means 2 times 1. 3 factorial means 3 times 2 times 1. And if you're doing this without a calculator, you actually get some pretty convenient cancelling going on. I can see on top I've got a 3 times 2 times 1, and on the bottom I've got a 3 times 2 times 1. So I can cancel those and just work out what's left. And in this case, I've got 5 times 4 on the top, which is 20, 2 times 1 on the bottom, which is 2, and 20 divided by 2 gives me 10. So what does that tell me? Well, that tells me that if I'm in a situation where I'm doing 5 trials and I want to know how many different ways I can get 2 successes out of 5, well, there's actually going to be 10 different combinations that give me 2 successes out of 5 trials. Right, which I could have worked out by other means. I could have tried to list them all out. You know, I could have had like success, success, then fail, 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 and then tried to work out all the different combinations of that. But obviously that would take me quite a lot of time, whereas this formula's got me there pretty quickly. So this formula tells you the number of ways, right, that you can get the desired number of successes from a particular number of trials. Okay, now, as I said, in most cases, you won't need to know how to apply that formula. It's pretty rare that that comes up on exams, but it's good to understand it. There are, however, 4 cases that you probably need to know without a calculator and that they can come up. Right, now, these 4 cases are shown here. The first one is that if you have a number of trials and you want to know how many different ways you can get 0 successes, well, that will always equal 1, right? Because the only way you can get 0 successes is if every trial is a failure, and that only has like one way of occurring, one combination that will give you 0 successes, and that calculation there, n choose 0, is always equal 1. Likewise, n choose n just means you want all of the trials to be successes, and that will always equal 1 as well. If you want one success out of n trials, there will be n combinations, n different ways that can happen. So in other words, n choose 1 is always going to equal n. It's like saying, if I have 10 trials and I want one success, well then there'll be 10 ways that can happen. And this one here is kind of just the flipped around version of that. It says if you have n trials and you want all successes except for one, then there will be n different ways that can happen. So for example, if I had 20 trials and I wanted 19 successes, then there would be 20 ways that can happen. Right, so n choose n minus 1 is always going to equal n. So this might be a handy thing to just have in your summary book somewhere. All right. There is a bit to get through in this section. So this is the binomial probability formula. And what this is a way of representing the probability that you will get any particular number of successes when you conduct n trials of a binomial distribution. So let's have a look at this formula. The first part just says that it's n choose x. This first part of the formula is going to tell us how many different arrangements we have for getting the number of successes that we want. The second part of this formula is the probability of success to the power of the number of successes you want or need. And then the third part is the probability of failure, so 1 minus p, times, or sorry, not times, to the power of the number of failures. N minus x just means the number of trials that are not successes. So it's really a three-part formula. This is the number of ways you can get the number of arrangements to get the number of successes you want. This is the probability of success to the power of how many successes you want. This is the probability of failure to the power of how many failures you want. Okay, thankfully, and I know there's a lot of theory in this bit, we haven't even got to examples yet. Thankfully, there's two really pretty quick ways that you can calculate binomial probabilities on your calculator. The first way is if the question is just asking you for a specific number of successes, not a more than or less than, but like you want 2 successes out of 4 or something like that. And in that case, the buttons are interactive, distribution, discrete, binomial Pdf. Right, and there's some screenshots here that you can kind of refer to, and we're going to do an example where we use this in a moment. The second sort of option that you might use is if there's a range for your number of successes. So if it's like you're tossing a coin 10 times and you want to get 6 or more heads or 4 or less tails or something like that, then you'll use the same sort of menu. You'll go interactive, distribution, discrete, but you'll use binomial CDF. The C stands for cumulative. So CDF is what you use when you have like a range of successes that you want. Again, we'll go through this in an example in a moment, and hopefully things will sort of come together. Okay, for example 4, we're going to try to do this non-calculator. So this is really more of a manual application of that binomial probability formula. And this example says the probability that a person aged 18 to 30 owns an iPhone is 1/3. 4 people aged 18 to 30 are selected randomly. So we're choosing 4 people. So n is equal to 4. It's like we're going to pick one person, then another, then another, then another. And the probability of success is 1/3. In other words, each time we choose a person at random, the probability that they're going to own an iPhone is 1/3. So that's our probability of success. So again, just to introduce the shorthand, let's say we're going to let x equal number of people who own an iPhone. Now, the probability that exactly 3 of these people own an iPhone, we can write as the probability that x equals 3. Right? And here we can actually apply our binomial formula. The first part of the formula is the number of arrangements, n choose x. So it's the number of trials choose the number of successes that we want. So in this case, we've got 4 trials and we want 3 successes. Okay? Then it's times by the probability of success, which is 1/3, to the power of how many successes you want, which is 3, times the probability of failure, so 1 minus p, which in this case is 2/3, to the power of the number of failures you want. Now, we've got 4 trials, we want 3 successes, so we actually want 1 failure, right? 4 minus 3 is 1. Now, it's redundant, but I'm going to write the power of 1 there, just so we can kind of see how this is a straight application of that formula that we had over the page. Okay, and you can look back and forth between the formula and that first line of working as many times as you need to convince yourself that this formula has just been applied directly to the values in this example. Okay, now if we're doing this question non-calculator, we're going to need to work out what this 4 choose 3 is. Thankfully, it's one of the cases that we said that we might just need to memorize. Right, sorry to flick back and forth between the pages here, but this is a situation, remember it was 4 choose 3. So this is actually this situation here where it's n choose n minus 1, and that always equals n. So 4 choose 3 will just equal 4. Okay, the reason that works, or one way you can think of it, is that if I want 3 successes out of 4, then really I want 1 failure out of 4, and there's really just like one spot that failure can go, right? So if I'm choosing 4 people, and I want 3 of them to have an iPhone, well, it could be that the first person doesn't have an iPhone and the next 3 do, or it could be that the second person didn't have the iPhone, it could be that the third person didn't have the iPhone, or it could be the fourth person that didn't have the iPhone. But there's 4 different spots that one failure can go, and that's why there's 4 different combinations. So 4 choose 3 is equal to 4, right? Or, and I keep getting sidetracked here, if you wanted to, you could also do 4 choose 3 as 4 factorial over 3 factorial times 1 factorial, and that would just equal 4 times 3 times 2 times 1 over 3 times 2 times 1 times 1. Oops, sorry, I'm running off the screen there. And you can see that the 3 times 2 times 1 is going to cancel with the 3 times 2 times 1. We're just going to be left with 4 over 1, right? Okay, so there's 4 different ways we can get this combination, or this number of successes. Then we've got times by 1/3 to the power of 3. Sorry, I shouldn't have done that. 1/3 to the power of 3 would be 1/3 times 1/3 times 1/3. So that's going to give us 1 over 27 times 2/3 to the power of 1, which is just 2/3. Right, so if I think of this as 4 over 1 times 1 over 27 times 2 over 3, well, I'm just going to get on top 4 times 1 times 2. On the bottom, 1 times 27 times 3. Now 27 times 3 gives me 81. Right, so the probability that exactly 3 of these people own an iPhone will be 8 over 81. Sorry for the abrupt cut there. I just realized that in example 4b, I've made a bit of a mistake. This probably should be a calculator question. So let's leave example 4b. We're going to come back to that, and we'll do it as a calculator question. But let's look at example 5. It's another binomial question, but this time we can practice using our calculator. So this question says, it is known that the probability of a particular drug causing side effects in a person is 0.2. If a random sample of 10 people taking the drug are interviewed, what is the probability that 2 of the people will experience side effects, or at least 2, and so on? So in this question, we've got a probability of success of 0.2. In this strange world, apparently, having side effects from a drug is considered success. And then we're taking a sample of 10 people, right? So this is telling us that n is equal to 10. All right, the probability that 2 of the people will experience side effects, again, if we say let x equal number of people with side effects, so we define our variable at the beginning, and x is a binomial variable, then we can say the probability that x is equal to 2. Now, if we're doing this on our calculator, this gives us a chance to practice a couple of those new features we talked about. So to bring up the binomial calculations, it's interactive, distribution, discrete. The reason you know it's discrete is a binomial distribution is an example of a discrete distribution because you can only have whole numbers of successes, like 1 success, 2 successes, 3 successes. It's not a situation where you can get like 1.7 successes, so that's why it's discrete. And then binomial Pdf, and we use Pdf because we want a specific number of successes. We want exactly 2 successes. So in this menu here, you get a button or a section to push for x, which is the number of successes that we want, which is 2. Num trial, as you'd expect, means the number of trials, which in this question was 10. And POS means probability of success, which is 0.2 for this question. And we get our calculation. So the probability of getting 2 successes out of 10, when the probability of success is 0.2, is equal to 0.3019, and so on. Now, I'm not having much luck here because, again, I've written a bad example. It doesn't tell us how many decimal places to round to. Let's go to 4 decimal places. So it would be 30198, which is actually going to round up to 3020. Right, so a question like this, a good question, will tell you what to round to. Let's just say we've assumed it's 4 decimal places. Okay, the next part of the question says, what's the probability that at least 2 people will experience side effects? So not exactly 2, but at least 2. So we can write that as the probability that x is greater than or equal to 2. And again, we're going to work this out in our calculator. Without the calculator, this would be a really nasty thing to try to work out. We'd have to try to work out the probability that we get 2 people, then the probability that we get 3, then the probability of 4, probability of 5, all the way up to 10, and add those probabilities together. But with our calculator, it's a much more straightforward scenario. So again, it's interactive, distribution, and discrete. This time though, it's binomial CDF. We use binomial CDF when we have a range of successes. So this one said essentially 2 or more, and that's when we use binomial CDF. And you'll notice here that you get this lower and upper option. Now, this is for the number of successes. So we wanted at least 2. So we want 2 or more. The upper is 10 because that's the most we can get. It's 10 people. So the most people we can get, the most successes we can get is 10. Number of trials is 10, and the probability of success is 0.2. We hit OK, and we get 0.62419. All right, so again, if we go to 4 decimal places, that'll be 0.6242. Right. As you'd expect, that probability is higher because in the second case, we've actually got more different ways we can get this particular probability, because we can get 2 people or 3 people or 4 people and all the way up to 10, whereas this one was only allowing us to get 2 people. So it makes sense that the first calculation was a smaller probability than the second one. Okay, part 3 of the question says, what's the probability that the first 2 people interviewed will experience side effects? Now, this is a bit of a tricky one because it's talking about a specific order and just saying that the first 2 people interviewed. So it's not really talking about the number of successes out of 10. It's actually just saying that if we have 2 people interviewed, we want to know the probability that they'll both have side effects. It's actually a little bit of a trick question because it's sort of taking you out of binomial and just saying, well, probability that we get, let's say, side effects, then side effects when we interview 2 people would just be 0.2 times 0.2. We just want the first 2 people. We don't really care what happens after that, so we don't have to consider the next 8 people. We're just thinking the first 2 people experiencing side effects, so 0.2 times 0.2, which is 0.04. So watch out for that sort of thing. Sometimes a question will kind of almost lead you down the path of being binomial calculations on your CAS, but then there'll be a question where it's maybe more specific or about things happening in a particular order, where you can actually use a different method and sometimes an easier method to get to the answer. Okay, now as promised, I'm going to go back to example 4b here. Right, so this was my fault. I wrote this example, and 4b, without a calculator, it's possible, but it's pretty horrible, and it certainly wasn't intended to be this horrible. So we're going to do example 4b, but with a calculator. So just to quickly remind you, this was a situation where we had 4 people, 4 trials. The probability of success, which was owning an iPhone, is 1/3. And the question B said, given that at least 1 person in the sample owns an iPhone, find the probability that 2 or more people in the sample own an iPhone. All right, so remember that with these questions like this, when we see that phrase, given that, that's conditional probability, right? And so what it's saying is, we know that at least 1 person owns an iPhone in this sample, right? That's our condition here. So given that we know that information, what's the probability that 2 or more people in the sample will own an iPhone? So even if you're not sure how you're going to go about calculating things, with a conditional probability question, if you write the information in this format, that then leads you to putting these values into the formula. And remember that the formula for conditional probability says it's the probability of both things. So x being greater than or equal to 2 and x being greater than or equal to 1 over the probability of the second thing, the probability of the condition that we know has occurred. Right, now when we get that far, we can look more closely at the top and say, okay, well, if we need people, we need at least 2 successes and at least 1 success. Well, the overlap there, the intersection, is just at least 2 successes, right? If we want at least 2 and at least 1, that really just means at least 2. So it's the probability that x is greater than or equal to 2 over the probability that x is greater than or equal to 1. And we can do that on our calculator, right? So remember, in this question, it's n is 4 and p is 1/3. And so we can actually set this up and go interactive, distribution, discrete. Now, both of these probabilities are greater than or equal to, so we're going to use binomial CDF. For the first one, we wanted more than 1. For the top one, we wanted more than 2. So we want 2 to 4 successes from 4 trials with a probability of success of 1/3. Okay, and we also wanted to, with our bottom number, know the probability of getting at least 1 success so same inputs there, but this time with a range of successes from 1 to 4, and we've got our 2 probabilities. So this will equal 0.407 continued over 0.802 continued, and remember that it's best not to round off until the very end. I'm just going to do 1 divided by the other in my calculator. 0.057, let's go to 4 decimal places, so 0.5077. So sorry that's jumped around a little bit there, but hopefully you've got a bit of a sense from example 4a about how we can set up binomial calculations without using our calculator. And from the remaining examples, you've got a sense of how you can start putting these into our calculator using Binomial Pdf and Binomial CDF. As always, let your teacher know if you've got some questions. This section is brand new and probably takes a fair bit of getting your head around things. So ask questions if you need help. But otherwise, good luck with exercise 14.8, and I'll see you in the next video.